Mike, with your approval, I will record and then post this video online for free, okay?
Sure.
Okay, yes, so let me make a brief introduction, okay? Hello, everyone. This is the third lecture, the last one of 2021 summer lecture series by Professor John Michael Kosterlitz, the 2016 Nobel laureate in physics. He will discuss the RG results for their theory on the Kosterlitz-Thales transition on superfluid transition in 2 dimensions. This work was sponsored by the Institute for Advanced Study of Suzhou University, and it is done as part of the summer activity by Professor Kosterlitz and myself in our own time. Both Professor Kosterlitz and I are faculties on the Brown University Physics Department. And so this work is in collaboration with Suzhou University. Mike, you are on your own.
Thank you very much. This is the third lecture on about superfluid helium films and related systems. And last lecture we derived what is called the renormalization group. And what I would like to do this last lecture is discuss some physical results. Well, by physical, I mean experimentally measurable results, which resulting from this peculiar renormalization group. Okay, so let's go to the first slide. If I can find my cursor, which I seem to, oh, there it is. Okay, so I think in the end of the last lecture, you saw these formulae because what we're doing is we're trying to calculate this thing called, on the top left, called K sub R of T, which is a renormalized or measured stiffness constant, which is proportional to the superfluid density, the renormalized superfluid density in 2 dimensions. And so we had an expression for this renormalized superfluid density. The first couple of terms as a perturbation expansion in the fugacity, the vortex fugacity Y. And so the idea is that this is expressed in terms of fluctuations, anti-vortex fluctuations over all length scales from A to infinity. A is the core size of a vortex. And so A is the smallest possible length scale in the system. And so you can express the renormalized, the inverse stiffness constant as this kth minus 1, which is just basically the coupling constant, plus a term in the proportional to the y square, or the square of the vortex fugacity. And then the idea of basically what we start with is an expression in the integral from A to infinity over integrated of the length. Now, the idea is very simple. What we do is we say, okay, we'd like to formally change our smallest length scale, A, to A, let A go to A times e to delta L, where delta L is a small change in the scaling parameter. And we want to write the integrand in terms of this new minimum length scale. And originally we had the minimum length scale with, in the denominator with this a to the power of 4 minus 2 pi k. So then we simply rewrite a as, the new length scale, new cutoff, a e to delta L to the power of 4 minus 2 pi k, then put in this factor e to the 4 minus 2 pi k delta L to cancel out the delta L to the, the e to delta L to the times 4 minus 2 pi k. And of course, there's and then there's a little piece, this 4 pi cubed y squared delta L, which is simply the integral from a to e to delta L of the same integrand. And this is just 4 pi cubed y squared of delta L. And so what we do is we combine this small correction, the 4 pi cubed y squared delta L, with the one over the coupling constant. So we write this is k minus 1 plus 4 pi cubed y squared delta L plus 4 pi cubed y squared, just the same coefficient that was in front of the original integral, and we have 1 plus 4 minus 2 pi k times delta L. That's just the expansion of this factor e to the 4 minus 2 pi k delta L times this integral from the new cutoff, a e to delta L to infinity, of the expression which was original expression, except a replaced by a e to delta L. And so we immediately see that the change in this, the change in this, in the inverse coupling constant, delta k to the minus 1, is just this little factor 4 pi cubed y squared delta L. And we rewrite all the junk as the coefficient of our new integral. It's just 4 pi cubed y squared times 1 plus 4 minus 2 pi k times delta L. And so this is the new fugacity squared. In other words, the change in the fugacity squared, delta y squared, is just equal to 4 minus 2 pi k times y squared delta L. Now, then the next bit of the renormalization trick is to regard the coupling constants k and y, regarding the system as a set of interacting vortices with fugacity y. And so we regard the coupling constants k and y as functions of the scale parameter L. And so we can simply say that these statements are equivalent to this pair of differential equations for the inverse of k as dk to the minus 1 dl. And that's just equal to 4 pi cubed y squared plus corrections of order y to the fourth, which we don't calculate. And we have the change in the fugacity, dy by dl is equal to 2 minus pi k of L times y of L plus terms of order y cubed. Okay, now I have been a little bit hand waving here, because those of you who are paying attention may have realized that implicitly I've assumed that the coupling constant that occurs in the integrand, this as a power, also becomes the original coupling constant k, becomes the new coupling constant k of L. Now, I haven't demonstrated that this actually works. And to show that, we have to look at determine what happens to the k in the power, in the r to 3 minus 2 pi k. That started, as r to the 3 minus 2 pi k naught. And then we have to convince ourselves that this k in the power law actually changes from the original k to k plus delta k. Now, to do that, you have to do an expansion to order y to the fourth. And it's not hard, but it's a lot of tedious algebra. And this was done in the original paper by David Nelson and myself, and it does work out. So you'll have to take my word for it. Okay, so the equations which at the bottom here, this dk to the minus 1 by dl and this dy by dl are what are called renormalization group equations. And these equations are certainly valid for small values of the fugacity. Their corrections, as I said, are higher order in the fugacity, and of course we're not calculating those. But we have to check that this approximation actually works. So let's move on to the next slide. Okay, now these are just how the pictures of how the parameters flow. The horizontal axis is k, which is proportional to 1 over the temperature, and the vertical axis is the fugacity y. And the direction and the lines indicate how the renormalization group, the parameters change as this parameter L, scaling parameter L, increases. And we see that the flows split up into two types. There's the flows in the bottom right-hand corner below that straight line, and all these flow as L gets larger and larger, they all flow to fugacity y equals 0. Now, the reason why this is interesting is because we can actually do real exact calculations when the fugacity is 0, because it's just the simple Gaussian problem, which is trivial. And so we can identify, as I was saying before, all Hamiltonians that start in the bottom right-hand corner as corresponding to being below TC. But of course, TC, the actual physical TC, depends on the fugacity, the initial fugacity y naught. And TC of y naught is represented by this straight line flowing into the point, the y equals 0 line. And all the flows where the fugacity eventually starts growing corresponds to temperatures above TC. Now, okay, so I've written down the flows for 3 regions. The bottom right-hand region corresponds to the integration constant C, positive, and this little t, which I call T minus TC over TC, is negative. In other words, that's below TC. Then we have the region 2, which is the region in the center of the picture, corresponds to C negative, and this T minus TC over TC positive, but less than 8 pi y naught. And then region 3 corresponds to the integration constant C positive, and this little t larger than this quantity 8 pi y naught. And so both those two regions, region 2 and 3, correspond to temperatures above TC. Okay, now what are some of the predictions? Okay, Now, the renormalized stiffness constant, or the measured stiffness constant, which is related, remember, to the superfluid, the measured superfluid density. This quantity depends on the initial value for the coupling constant K and the initial fugacity. And it's also equal to the same correlation function evaluated with the renormalized or the changed interaction, the parameters K of L and Y of L, where K of L and Y of L are given by the differential equations. And so we have that, in particular, the actual measured stiffness constant, which depends, remember, with proportion of the measured superfluid density. Oops, what happened there? Oh, there it is equal to the same quantity as a function of the renormalized parameters, as, you know, which are given by the differential equations on the previous slide. And in other words, it's equal to, you can calculate this quantity at any convenient value of the scaling parameter L. Now, remember that this equation like this is the content, is the whole content of a renormalization group. It just tells you that the same quantity, the physical quantity, is equal to an effective quantity given in terms of different coupling constants. And of course, somewhere you have to do a real calculation, because remember, we're trying to calculate the physical correlation function. And all the renormalization group does is relates this quantity to exactly the same quantity which is to be calculated with a Hamiltonian with different interaction parameters. So somewhere along the line, you have to do a real calculation. And that's where the main difficulty is. Now, in this particular case, if we're below TC, we know that this parameter Y as a function of the scaling parameter L, as L goes to infinity, does scale to 0. In other words, no vortices. Okay, so this can be written, this is equal to the same function as a function of the coupling constant at L equals infinity and the fugacity at L equals infinity. But if we're below TC, the fugacity L equals infinity is equal to 0. I'm sorry, the bracket got into the wrong, is in the wrong place, and I didn't notice that till just now. But this correlation function at 0 fugacity, means no vortices, is just equal to the coupling constant at L equals infinity, which is a solution, you know, of the renormalization group equations. And if we're below TC, this K of infinity is greater or equal to 2 over pi. If we're above TC, when this coupling constant K is less than 2 over pi, then the integral on the previous slide diverges, and the perturbation expansion in the fugacity diverges. But this divergent perturbation expansion can be overcome by the renormalization group procedure, where, remember, what we do is the problem is we have to calculate integrals from A to infinity, the physical cutoff to infinity. And so we rewrite this integral as an integral from A to the original microscopic cutoff to the new microscopic cutoff, plus integral from the new microscopic cutoff to infinity. And this is exactly equivalent to the renormalization group equations which, which I wrote down before. And so all the physics is reduced from nasty statistical mechanical calculations into solutions of these simple differential equations. And of course, which are easily soluble as long as the fugacity y is small enough. And as a bonus, we can also calculate how the free energy density, or the free energy per unit volume or unit area, in this case, scales with this parameter, with this scaling parameter L as well. And we get dF by dL is equal to 2F. 2 is the dimension d, minus this factor 2 pi times the square of the fugacity. And we'll come back to this equation later. Now, the first two equations have fixed points when the coupling constant k and the fugacity y become don't depend on this parameter L. In other words, the right-hand sides are 0. And there's a fixed point at pi k equals 2, right, when the dy by dl is 0, and of course also y equals 0 when dk to minus 1 by dl is 0. And what we can do is expand about this fixed point, these fixed points, by defining pi k is 2 plus x. And then we get equations for replacing, the k by x. We get dx by dl is minus 16 pi squared y squared plus terms of order xy squared and terms of y to order y to the fourth. So as long as the deviation of the fixed point is small enough, this equation is good enough. And we also have dy by dl is minus xy plus smaller terms. So then we can integrate these two equations simply by dividing one by the other to get an equation dx by dy is equal to 16 pi squared y squared divided by xy. And this solves, that equation can be easily integrated to get x squared minus 16 pi squared y squared is equal to some integration constant, which we're calling this constant c. And of course, this integration constants depend on the initial value of y and the initial deviation from tc. And one can show, after a bit of algebra, that this integration constant c is actually minus t, remember t is proportional to t minus tc, times 8 pi y naught minus t. And so you've got three regions. The first region is when c is greater or equal to 0. And if x, the deviation, if pi k minus 2 is greater than 4 pi y naught. And that, of course, is always positive. The second regime is when this integration constant c is negative. And the third region is where, again, this integration positive is c is greater than 0, but this x of L is smaller than minus 4 pi y. And these three regions need separate solutions. So it gets a bit tedious. Okay, so it's the first pair of equations become just dx by dl is minus 16 pi squared y squared plus other smaller terms, and dy by dl is minus xy. But remember, we've got the relation that x squared minus 16 pi squared y squared is equal to c, which is this minus t, times 8 pi y naught minus t. And so we can say that dx by dl is just c minus x squared by replacing y squared by c minus x squared. And we can integrate this equation. And we can easily integrate this thing to get L is equal to 1/2 twice the square root of this integration constant c times the integral from the initial value of x to the value of x to x of L of dx times 1/x plus root c minus 1/x minus root c. So that we can integrate that thing easily and get the solution of x of L is equal to root c times, okay, so I won't tell you any more about what this, but you see that it is this expression here. Now, of course, we can always say that the initial value of x at x naught, this is x at L equals 0, is positive. We're below TC, and x naught is much greater than the integration constant. This integration constant c vanishes at TC, 0 at TC. And so we can x naught is non-zero at TC. And so we can always say we're sufficiently close to TC, so this x naught we assume is much larger than the integration constant c. And so then we can write, instead of writing the full expression for x of L, we can write x of L equals x naught over 1 plus x naught L times 1 plus terms of order L root c. And this is fine, a good approximation, as long as 2L root c is less than 1. And if 2L root c is greater than 1, the approximation to this x of L is just root c plus terms which vanish as L goes to infinity. And so in other words, when L goes to infinity, this x of L becomes the square root of c. And remember, c is proportional to minus t. And so we can, now remember on the previous slide, I said there's a sort of crossover situation when L is the value where 2L root c is equal to 1, right? Because clearly that's where both the approximations here become bad. And so there's a special value of L, which is 2L root c is equal to 1, and I can call this value of L equal to 1/2 root c, call that special value L star, and I call the length scale, the real physical length scale, measured, of course, in units of the vortex core size. So this is a dimensionless length in units of the vortex core size. That's just e to the L star, which is where L star is 1/2 twice the square root of c. Now this length scale is a correlation length below TC. It also exists above TC, but this is the only length scale that exists below TC. And it's equal to the exponential of 1/2 twice the square root of mod t, this expression here. And it can be interpreted as the separation of the largest vortex-anti-vortex pair in the system, because all vortices and anti-vortices are bound in close pairs, okay, small pairs. And we can say that this E to L star is the length scale, or E to the L star is the length beyond which there are no vortex pairs. So in other words, if I simply coarse grain my system to this, where the shortest, where the only distances are larger than this one, then in this effective system, there are no vortices present. In other words, this length scale is the length scale of the largest vortex-anti-vortex pair. And we can approximate this thing in two different ways, depending on whether TC minus, mod T minus TC is smaller than 8 pi y naught or larger than 8 pi y naught. And so you see what we have here is this length scale diverges like 1 over the square root of TC minus T. If TC minus T is small enough. And if TC minus T is larger, this thing behaves like 1 over twice the magnitude of T. And by the same token, if we're below TC, we can write the measured stiffness constant as this, and y of infinity below TC is 0. So this is just the coupling constant k as ideal infinity, and this works out to be 1 over pi times 2 plus the square root of c. But of course, remember that this quantity, this kr of t, contains the superfluid density. And so we can, it's proportional to rho s of t divided by t. So therefore, the measured superfluid density, mass per unit area divided by temperature is equal to m squared times Boltzmann's constant divided by pi h bar squared times 2 plus this square root. That's when t is close enough to TC. Now, the important point is that, and this is particularly true when we're at TC, in other words, where little t is 0. And the important point is that this prediction is an exact and inescapable prediction for t less than TC and t equals TC within the theory. And technically, the reason why this is an exact prediction is because the renormalization group of variables we're working with are what are called marginally irrelevant. And so that the perturbation expansion in the fugacity has a chance of converging. A standard perturbation expansion cannot converge because it's a singular, it's an expansion in the coupling, and a standard perturbation expansion is an expansion in the coupling constant, and those expansions are all about about very singular points, essential singularities in the coupling constant, and therefore conventional perturbation expansions are at best asymptotic. They cannot converge. But this is a different perturbation expansion because it's in this marginally irrelevant variable y, which tends to 0 at TC and below TC, and therefore it has the perturbation expansion actually has a chance of converging. I think it does converge, but I'm not able to, I'm not knowledgeable enough to prove that, but I'm convinced that the perturbation expansion is actually convergent if we're below TC. And therefore this prediction for this superfluid density as a function of temperature divided by temperature equal to this expression here is basically exact. And it is a smoking gun prediction at TC, which is due to Nelson Kosterlitz in a Fizerov letter written in 1977, this can be, or 78, this can be verified or contradicted by experiment, because the superfluid density divided by temperature is experimentally measurable, at least experimentally accessible. And this measurement was made in 1977 by David Bishop and John Reppy at Cornell University. It is shown in the next slide. Oops. There it is. Okay, so this is the superfluid density just below TC. Okay, and it's in units of grams per unit centimeter, per square centimeter. And this is the superfluid density just below TC as a function of TC. Now you may say to yourself, how on earth can I make TC, the critical temperature, a parameter? Well, it's easy, because if you want to increase TC, all you do is you make your film thicker. And if you want to reduce TC, you simply make the film thinner. And so you can vary TC this way. It's very easy. And so you can, the theoretical prediction for rho S, the superfluid density just below TC is equal to, or divided by TC, is exactly this this solid line, which is the slope is predicted by the Kosterlitz, beg your pardon, the Nelson-Kosterlitz prediction, and the experimental points, different experiments. There's the Bishop-Reppy experiment, and there's various third sound measurements, and these points are all, for different experiments, are all scattered about the straight line, the theoretical prediction. Okay, so then let's go on a bit. Okay, then let's think about the region 2, just above TC, where the fractional deviation from the critical temperature is small enough, because then this integration constant C is negative, and so we have 16 pi squared y squared is equal to x squared plus the magnitude of C. And we can integrate the equation for x. And we find that we get minus L is equal to 1 over the square root of the magnitude of C times the inverse tangent of x of L over root C minus the inverse tangent of x naught over root C, of root mod C. Now, of course, this x naught is positive, but as L changes, the effective coupling constant K of L decreases. So x of L goes through 0 and becomes negative. When L gets larger, this x of L can be taken to be negative. And so now, in order to use this equation, we have to decide on a value of this upper limit of integration, L. Now, what is the value of what sort of, or if you like, in this case, we've got to decide on what is the value of x when L is, when the value of L is large. And so we can take the upper limit of integration at L equals, say, called L plus, where x of L plus is just minus x naught. And where x naught, remember, is the initial value of x. And we can also assume, of course, that x naught divided by the square root of mod C is large. Therefore, the inverse tangent of x of L plus divided by the square root of mod C, remember x of L plus is negative, so this is minus pi over 2, because the inverse tangent of you know, minus something very large and negative, it's just minus pi over 2. And the initial value of is inverse tangent x naught over this root mod c is just plus pi over 2. And so therefore we can say that this allows us to define a correlation length, a length scale above TC, which I call psi plus, which is equal to e to the L plus, which is e to the, because we defined L plus to be 1 over root mod c times minus pi over 2 minus pi over 2. In other words, that so the e to the L plus we can call e to the pi mod c to the square root of pi times 1 over the square root of mod c. And so this correlation length, which is above TC, is equal to the correlation length we evaluated earlier to the power of 2 pi. And we can interpret this correlation length psi plus as above TC as the largest distance, the largest length scale that for which we can regard vortex anti-vortex pair as being bound. So in other words, at length scales less than this correlation length, psi plus, the system behaves just as if it was below TC. And so then this allows us to define the stiffness constant. Now remember, the stiffness constant we defined before was a function of the interaction constant K naught and the fugacity. But that's a bit difficult if we're above TC. So let's introduce as a function of Q, which is just the Fourier variable. So this can be written as a coupling constant minus 4 pi squared times x squared of the coupling constant times the expectation value of the vortex density, or the Fourier transform of the vortex density, n of q times n of minus q divided by q squared. And remember, this is the same thing as the renormalized stiffness constant as a function of the scaled q, which is just q e to the L, k of L, and y of L. So we've got this expression at the top, right? Now we can calculate this thing. You remember, we want to evaluate this quantity above TC. But the problem is that we're going to try to evaluate it at length scale L. Okay. But we know that the fugacity y of L is getting larger. In other words, we've got a lot of vortices present. So we can say, okay, if we want to evaluate this quantity, the simplest thing to do is to try to evaluate this thing at when L is such that this vortex fugacity, y of L, has grown to large, has grown to significant values. And when the fugacity is order 1, that means it's a system of dense vortices and anti-vortices. And so what we can do is we can evaluate this thing approximately at the length scale e to the L star, so it should be L star, not I star, sorry, by, how do we do that? Because what we have here is a set of, we've got a plasma of charges, if you wish, all interacting with the Coulomb interaction. And so how do we treat a dense plasma? We can treat it by the Debye-Huckel approximation. Okay, so we can calculate this renormalized stiffness constant as a function of the Fourier variable Q as K of L star time minus 4 pi squared K squared of L star divided by Q e to the L star squared times the vortex correlation function, vorticity correlation function at this value of Q e to the L star. But e to the L star is the correlation length, this psi plus. And we can evaluate this expectation value in the Coulomb gas ensemble with the Hamiltonian, with this Hamiltonian here. And this is easy to use because this B of L is related to minus the logarithm of the fugacity at L star. But since we've said that the fugacity has grown, so it's somewhere between 0 and 1, I can choose this B of L star to be some number. And we can calculate this correlation function by Huckel approximation. And so this correlation function is just 1 over the coefficient in the Hamiltonian of n of k, n of minus k. So, but calculated at k equals q times the correlation length. So we get B of L star, K of L star divided by B of L star plus 4 pi squared K of L star divided by Q psi plus all squared. And when Q, let's now assume that we're at very small values of Q. Now it's large, looking at long length scales. So we can take Q times psi plus going to as a small quantity. So in other words, this expression here behaves like Q psi plus all squared. And when and of course the superfluid density is related to this correlation length, this correlation function at Q equals 0. So we have, if we're above TC, we get that we can simply put Q psi plus to 0, and then then this right-hand side goes to 0. Let's have in this expression here, we've got this term goes to infinity. We've got 1 over 0, right? Therefore, this renormalized coupling constant or correlation function is equal to 0 if T is greater than Tc. And this tells us that the superfluid density vanishes if T is greater than Tc, which is exactly what you expect, of course. But it's nice to see a physical expectation borne out by a calculation. Now, maybe I could talk for a few minutes, because we can also calculate the order parameter correlation function, which is called G of R and G of R and T. And this is the expectation value of e to the I theta r minus theta of naught. And this quantity, this function, obeys the renormalization group equation. If I call this thing G of naught, at L equals naught, and I want to know calculate the equivalent quantity at length scale L, I have this correlation function obeys the equation dg by dl is d minus 2, which in our case is 0, minus plus 8 of L times G of L. And so it's, then I can integrate this thing. And I get G of L is G naught times, yeah, I can't read my own slides because I got pictures. Oh, that's it, yeah. Sorry, I've got, here we go, right. Now this 8 of L is just 1 over 2 pi k of L. This is easy to see because in if you just take a Gaussian system, the correlation function decays like 1 over r to the power of eta. And eta is exactly 1 over 2 pi k. But near the critical temperature, or near the fixed point, this, remember, we know what pi k of L is. And 1 over 2 pi k of L is approximately a quarter minus x of L over 8, plus higher order terms, where x, remember, is the deviation from of pi k from 2. Now, the content of the renormalization group analysis is a relation of the physical quantity, Green's function or correlation function, to the correlation function at the scale L, times this factor e to the minus integral 0 to L dl prime eta of L prime. And this and this is the physical correlation function we want to know. And so we have to know something about, in order to calculate it, we have to know something about the correlation function at scale L. But this is easy to, it's actually, and this correlation function is calculated with the effective Hamiltonian. Now, the argument is as follows. Suppose we're at Tc, T is equal to Tc. And then we have to evaluate this, this new correlation function at some carefully selected value of L. Now the point is, if we're at Tc, the shortest length scale is just R of L, the distance at length scale L, which is equal to the original distance times e to the minus L. And we can choose this, this value of L such that R e to the minus L is just one lattice spacing. Then this nasty G, let's call it this thing just G of L. This G of L is the correlation function of where the separation is just one lattice spacing times k of L, y of L, but it doesn't matter because if we've got two, let's say, spins, one lattice distance apart, and we assume they're interacting ferromagnetically, they're going to be parallel to each other. So this G of L is going to be just one. So in other words, what we have is the two-point correlation function is just going to be this thing, which is basically, just this. Okay, never mind the math. It is just the separation to the minus 8 of t, where 8 of t is just 1 over 2 pi k. That's a trivial calculation. And so what we get is that the correlation function can be written as exponential of this integral over L, but with the upper limit being just the logarithm of the separation R. And if we're close to TC, this can be written as e to the minus L over 4 plus 1/8 integral 0 to log R of dl times the x of L. Remember, x of L is the deviation of pi k from 2. And so this integral is, okay, you can do the integral, and it's just equal to root CL plus some correction. And therefore, what we end up with is the spin-spin correlation function as a function of R and T has got two forms. We have either R to the minus 8 of T times the logarithm of R to the power of 1/8. And this is true for both the separation R and the correlation length scale, much larger than 1. But here we must have R is small compared to this correlation length. And if the inequality is reversed, where R is larger than the correlation length, this is just R to the minus 8 of T. And this 8 of T is just 1 over the K of R, the normalized coupling constant at T. And this is equal to, it's linear in temperature if we're at very low temperatures. And if we're slightly below TC, it's a quarter minus this temperature dependent quantity. I don't want to, you can do these, you can check all these calculations for yourselves. It's a nice exercise. And if we're above TC, we have the same relationship, but the problem is we don't know what this effective correlation function is. And when, okay, so when the separation is much larger than the correlation length above TC, this psi plus of T, we can choose L is equal to the logarithm of psi plus, and we expect that the correlation function, G of R of psi plus time, and as a function of the K of at L, at, where L is log psi plus and Y of at log psi plus of order behaves like e to the minus R over T. Minus R over the correlation length. So we expect that the correlation function behaves like e to the minus, I beg your pardon, there should be a minus sign there, R of psi plus times another correction factor, which is unimportant. Okay, so the conclusions are, we expect the spin-spin correlation function to look like e to the minus R of psi plus for very large separations. And when R is smaller than psi plus, we expect it to behave like R to the minus quarter for the separation lying between psi minus and psi plus. And if R is smaller than psi plus, but still large, this should behave like R to the minus quarter times log R to the 8th. In other words, for length scales less than this correlation length, the system behaves just like as if it was below TC. Okay, now, so I think I better stop there because this was just a Okay, this is I just thought I'd do this calculation of the spin-spin correlation function when the Hamiltonian can be written as k over 2 times the sum of nearest neighbor pairs, theta I minus theta j squared. And therefore, the correlation, the spin-spin correlation function, when Ri minus Rj is very large, can be written, like this. And it's not very difficult. It's not very hard to do these integrations. And we use, this is the 0th order Bessel function, and we use that, we can approximate this thing that J naught of QR is about 1 when QR is less than 1, and it's 0 when QR is greater than 1. So this spin-spin correlation function behaves like Ri mod R minus Rj to the minus 8 of t, where 8 of t is just 1 over 2 pi k. That's the origin of, as I said, the origin of, okay. Now, I don't think I've got time to talk about the specific heat, but one can calculate the specific heat. And this is quite interesting because let me just explain what's going on. The specific heat behaves like 1 over the correlation length, 1 over the correlation length squared, above TC, above TC. And this behaves, of course, like e to the minus a constant times t to the 1 over the square root of t minus TC. And it behaves the same way for below TC. So in other words, the specific heat has an unobservable essential singularity at TC. You can't see it because it's vanishingly small. But there is a rounded maximum in the specific heat about 40% above the critical temperature. And so actually the specific heat of this system looks something like this. This is actually a picture from lots of people have estimated the specific heat. We got, Sola and Riedel, and we also David Nelson, of course, has estimated the specific heat. But everybody agrees that it's of this form with a critical point. The actual phase transition happens there at this star. When the specific heat is just growing, but the peak occurs well above the critical temperature. And the reason for this is that the specific heat is actually the vortex specific heat. And so it's due to what's happening is that the entropy is being released, and it's the entropy of the vortices. Now, at the phase transition is governed by the largest vortex-anti-vortex pairs, and there are very, very few of them. So in other words, at the transition, it's the very large vortex-anti-vortex pairs sort of unbind, but there are very few of them, so there's very little entropy involved. Therefore, that's why the specific heat is so smooth actually at TC. And it's when you're well above TC, when the smallest vortex-anti-vortex pairs unbind, because those are the smallest pairs there are more small pairs than any other size of pairs. And therefore, the most entropy is released when the smallest pairs unbind. And this happens well above TC. And of course, so that what you see is this rounded peak, because there's nothing non-analytic, no phase transition here. This is just a smooth change in the specific heat as a function of temperature. But this is where the most entropy is released. So this is where the peak in the specific heat is, and it's just a rounded one, some 40% or so above TC. Because all the non-analytic singular behavior happens, this unobservable essential singularity. And so so this is something else which I have on the slides, but you're not interested in hearing about this. So that's really the end of my talk, where I've talked about some of the consequences of the vortex theory and the predictions. Some of the predictions are experimentally measurable, and basically can be measured very accurately, and there's agrees with the theoretical prediction. And there are some various other predictions one can make which are not really experimentally measurable. After all, it's not easy to measure the specific heat of a thin film of superfluid helium. But if you could do it, it would look something like this. And the non-analytic behavior at the phase transition is just some unobservable essential singularity in temperature. And so I guess that's the end of the 3 lectures. And I have tried to explain how this vortex theory arose and what the predictions from it are, and try to explain what sort of things you can get out of it. And so really, that's the end of the course, and I hope there's some questions from those who have students who have been listening.
Okay, thank you, Mike. Okay, so the talk is open for question, but may I ask a question first?
Of course.
Okay, so so if you go back your slide to the projection for the superfluid density versus temperature. The experimental data, the Bishop Repi data. Okay.
Here we go. Yeah.
Okay, this one. Okay, so so this line is a line with no free parameters from
No
your
free
theory.
parameters. Yeah, sorry, I forgot to say that.
Okay, so this is the most striking aspect.
Yeah.
Okay, so if you go back to one more slide, which you went through very quickly.
Well, this one?
Yes, this is the slide. Okay, so that slope, in fact, is this 2m squared kb over pi h bar squared, right?
Right.
So the slope has the is determined by Boltzmann constant, the mass of the helium atom, and the Boltzmann and the Planck constant.
Yep.
Okay.
Yeah.
So
also this prediction is inescapable. I mean, from within the theory, so that there's no way.
So I found that this is very striking, because the last time we see that a theory with many approximations, and then that led to an exact result, was the solution of a hydrogen atom, right? So where we did it, when we solved the central potential problem, we solved the Schrodinger equation, and then you get the energy levels, you get the set of the quantization by set up the boundary conditions. Boom, you get the exact result for the energy levels, quantized energy levels. And those are exact, and that was tested experimentally to very high precision. Here, we have a many-body system that you almost have the same kind of level of approximation along the way, yet you arrive at something exact.
Yeah, right. But I like to say that this is an exact prediction from an approximate theory.
Okay, so what made this work? So is the topological invariant nature of the vortices?
No, I think maybe people have different opinions, but I think it's a consequence of the fact that within renormalization group theory, at the critical point, the physics is determined by the fixed point, and the fixed point does not depend on the initial physical Hamiltonian. There are many, many different Hamiltonians that will flow to the same fixed point. And so the superfluid density depends on the fixed point.
And the physical point is
not on the details. Because you see, at the fixed point, or in the vicinity of the fixed point, the only parameters that survive are this coupling constant K, and that at the fixed point takes on a particular value.
Mm-hmm.
And then the other thing about the fixed point is the fugacity Y is 0.
Mm-hmm. So what I'm trying to say is, if we step away from all these mathematical details, and then let's ask from the original Hamiltonian of the problem and the symmetry of the problem of the system. So where what is the origin of this fixed point in terms of the original physical Hamiltonian, the Hamiltonian of original physical system?
We're a bit far from that, because the point is that the initial assumption or guess is that I can describe the long distance behavior, which is what we're interested in terms of a theory which involves only spin waves and vortices.
Mm-hmm.
And so, and the point is that the vortex part, the renormalization group tells you that the critical point, this awkward bit, the fugacity, is 0.
Mm-hmm.
So in other words, lots and lots of junk, which was in the initial Hamiltonian, has been thrown away. It's simply not there anymore.
They are irrelevant, basically.
It's irrelevant. And so the only thing that matters is really this sort of renormalized coupling constant, which takes on this very special value of 2/pi at the fixed point.
Mm-hmm.
And so that's why you get, in the expression, mm-hmm. Because you have these physical parameters like Boltzmann's constant, Planck's constant. They're just there because they're there in the theory. Mm-hmm. And so they're around because of if you like, a dimensional demands. And the only thing that comes out of the calculation is the 2/pi. That's what the renormalization group tells you. That the proportionality constant is this 2/pi.
Mm-hmm. Sure, on the mic. They actually have some. We also have some questions from the audience.
Okay.
The first one is from last session. I think the gentleman said, I believe there's an analogy between the laughing state and the plasma in the context of fractional quantum Hall effect. And it looks very familiar to the vortex Hamiltonian. He wonders, Could you comment on the connection between quantum Hall effect and vortex dynamics?
Well, there's very little, because the quantum Hall system is very different in the sense that, I mean, okay, I have hardly used quantum mechanics at all. The only place where quantum mechanics comes in is really that the superfluid film can be defined by, can be written in terms of a complex field, a bosonic field, right? And so I can say that, as far as I'm concerned, it's a classical field, and the only bit of quantum mechanics comes in that this field's a complex field, so it's got a magnitude and a phase. Beyond that, the theory is purely classical.
Okay. I hope that answers the question to the audience.
Yeah.
There's one more question. I mean, could you comment on the non-perturbative effect in the physics of vortex?
I'm sorry, on the what effect?
Non-perturbative.
Okay, well, all right. One
Can you
could
rephrase, Mike, can you rephrase the question? I don't quite understand the question.
well,
Here, going to ask whether there's any non-perturbative effect in the physics of vortexes.
well, I mean, the whole effect is essentially non-perturbative, because the only place that perturbation theory is used here is in this an expansion in powers of the fugacity. So assuming that the fugacity is a small quantity, so therefore one can write down in principle a perturbation expansion in powers of the fugacity. Now, the very pretty thing is that this fugacity, if it vanishes, if we're just below TC, so it goes to 0, and therefore it's a problem with zero. There's nothing in the theory anymore, except for the smooth, these smooth third sound modes in the system. So really it becomes, what the theory is saying, it's a very simple system at TC.
I think this is a very good question, Mike. Let me follow up on this question.
Well, there's one interesting thing, and that is that there's one, at the time it was a bit strange because people were arguing, look, we know that the superfluid density goes to 0 at TC. Now, as you get closer and closer to TC, the superfluid density gets smaller and smaller, and it vanishes continuously at TC. Now, that's fine, but that's true in 3 dimensions. But in 2 dimensions, it's something quite different, because after all, we're talking about a very thin film, where we're basically assuming that if we, that the film is the same over the whole thickness. There's no variation in the direction perpendicular to the film, and so we can argue, as I said, that the quantum mechanics comes in that the field describing the superfluid film is a complex field. That's that's all the quantum mechanics tells us. Well, of course, the other thing is of course, we use quantum mechanics to say the circulation of vortex is in unit. There's Planck's constant. No. There's H bars and so on and so forth. comes into the circulation of a vortex. It's quantized. So there's some more quantum mechanics. But that's always saying that, you know, the simplest vorticity, the lowest vorticity is 1, and then we've got the next vorticity is 2. It's quantized in units.
So this H bar survived to this point in this equation. It has
always there.
Originated from the definition of vorticity, isn't it? The quantum mechanical definition of vorticity. So in that sense, it comes from the phase description of the superfluid.
Yes, because you know, unit vortex is you know, when I walk around the vortex core, the change of the phase is just 2 plus or minus 2 pi.
Okay, so to follow up with this person's question in terms of a non-perturbative effect, I think he or she.
I mean, in one sense, that is a non-perturbative effect.
Okay, so either the vortex comes in 1 unit of 1 or 0, right? There's not like a 1/8 of a vortex in the system.
Right. No. So in that sense, it's very non-perturbative.
Yeah. Okay.
Of course, I wasn't thinking in terms of that because the actual calculation is perturbative in the sense that we're doing an expansion in powers of the vortex fugacity. But of course, when one talks about perturbation theory, one usually thinks, well, I forgot that one's often thinking that, you know, it's, you know, the perturbation theory goes much deeper than that. So, I mean, if you like, you could say that the fugacity is basically e to the minus vortex core energy divided by kT. And so you're already doing an expansion in something which is very, very singular. So in that sense is non-perturbative. But, you know, that's a bit of a, what I say, that's just more a play on words, because if you're doing a perturbation expansion on something, you have to, first of all, figure out what is your small parameter. You know, it's not necessarily a coupling constant, right? Here, the small parameter is the vortex fugacity, which already, you know, a highly singular thing. At least, you know, it's very singular it behaves like 1 over temperature. The exponential of minus 1 over temperature.
Okay, excellent. Okay, Martin, any more questions from the audience?
So far, I think the audience is happy with the great answer, I suppose.
Okay, so right now, so right now it's 20 past 10, it's way past Professor Kosterlitz's sleep time. So let's thank Professor Kosterlitz for the 3 wonderful lectures of 2021. And we look forward to 2022. Okay, let's thank Professor Kosterlitz one more time. Okay, thank you, Mike. You are done for this year. Okay.
You're very welcome.
Thank you, Mike.
Yeah,
thank you.
Yeah, it was fun.
Yeah. Okay.
Yeah.
I'm gonna stop recording. Okay.
Okay.
Yeah.
And I sort of feel that it would be